The ability to soar through the air, to defy gravity itself, is surely one of nature's most wondrous achievements. It grants access to new realms, new food sources, and a unique perspective on the world below. Yet, for all its advantages, true powered flight is an incredibly exclusive club. In the vast, sprawling epic of life on Earth, spanning billions of years and countless species, this extraordinary adaptation has evolved on only 4 separate occasions. First came the insects, tiny pioneers of the air. Then, the magnificent pterosaurs, reptilian giants that commanded the prehistoric skies. They were followed by the birds, descendants of dinosaurs, who fill our world with song and color. And finally, the bats, the only mammals to truly conquer the night sky. This remarkable scarcity speaks volumes about the sheer difficulty of the task. Flight is not a simple tweak or a minor adjustment to an existing body plan. It is one of the most complex and energetically demanding forms of locomotion ever to have appeared. It requires a perfect storm of anatomical, physiological, and environmental conditions to align. The journey from a terrestrial existence to an aerial one is fraught with immense challenges, a biological mountain so steep that very few lineages have ever managed to scale its peak. So the question we must ask is why? Why, in a world teeming with life, has this incredible superpower remained so rare? Today we will journey through the evolutionary labyrinth to understand the immense hurdles that stand in the way of taking to the skies. We will explore the profound biological costs, the engineering marvels required, and the unique pressures that can just occasionally push life to achieve the impossible. This is the story of evolution's ultimate challenge, the invention of flight. To evolve flight is not merely to sprout wings, it is to fundamentally reinvent the entire body from the inside out. Consider the skeleton. For a land dweller, bones are pillars of support designed to withstand the constant compressive force of gravity. But for an aspiring flyer, this same skeleton becomes a lead weight. It must be completely re-engineered, becoming a marvel of lightweight construction. Bones must become hollow, thin, and fused together for rigidity without adding mass. A delicate balance between strength and airiness that most animal blueprints simply cannot accommodate. This is a total system overhaul, not an optional upgrade. But the transformation goes far deeper than just bone. The muscular system must undergo a revolution. Enormous pectoral muscles, sometimes accounting for a significant fraction of the entire body's weight, are needed to power the downstroke, the crucial movement that generates lift. These muscles, in turn, require massive attachment points like the keel on a bird's sternum, a feature entirely absent in their terrestrial relatives. The nervous system, too, must adapt, developing the lightning-fast reflexes and sophisticated spatial awareness necessary to navigate a three-dimensional world in motion, processing information at a speed that would be unimaginable for an animal on the ground. And then there are the internal systems, the hidden machinery of life. The respiratory system must become super efficient, capable of extracting vast amounts of oxygen from the air to fuel the furnace of flight. Birds, for instance, developed a unique system of one-way airflow with air sacs that allows for continuous oxygen absorption, even while exhaling. The circulatory system must be a high-pressure powerhouse with a large, powerful heart to pump oxygenated blood to those demanding flight muscles. Every single part of the animal, from its largest bone to its smallest cell, must be conscripted and redesigned for a single, all-consuming purpose: to take to the air. The sheer energetic cost of flight is perhaps the single greatest barrier to its evolution. Staying airborne is the metabolic equivalent of running a marathon that never ends. The power output required is immense, far exceeding that of walking or running. This creates an unforgiving economic reality. An animal must be able to find and consume enough fuel to pay this staggering energy bill. For most species, the cost is simply too high. The daily search for food is already a challenge. Adding the colossal energy demands of flight would lead to a swift and certain bankruptcy. This is why the vast majority of flying animals are small. A smaller body requires less energy to lift and keep aloft. Insects, bats, and most birds operate within a size range where the power-to-weight ratio remains favorable. As an animal gets larger, the physics of flight become exponentially more difficult. The weight increases faster than the muscle power required to lift it, a principle known as scaling. This is why we don't see flying elephants or rhinos. Their bodies are simply too massive, and their metabolic engines, while powerful, are not equipped for the sustained, explosive output that flight would demand. Even for those animals that can afford it, flight dictates their entire lifestyle. They must be incredibly efficient hunters and foragers. A hummingbird, for example, must consume its own body weight in nectar every single day. Its life a frantic, continuous search for the next high-energy meal. A swift can spend almost its entire life on the wing, eating, drinking, and even sleeping in the air. This specialization is a double-edged sword. While it grants them mastery of the skies, it also traps them. They have paid for their wings with their versatility, committing their entire existence to fueling one of the most expensive activities in the natural world. Creating a wing is an extraordinary feat of biological engineering. A wing must satisfy two opposing requirements. It must be immensely strong to withstand the powerful forces of flight, yet it must also be incredibly light. A heavy wing would require too much energy to flap, making flight impossible. This paradox is a formidable evolutionary hurdle. The materials available to life, bone, keratin, chitin, and membrane, must be sculpted into a structure that is both a powerful aerofoil and a lightweight appendage. It's a problem that has been solved in different but equally brilliant ways. In birds, the solution lies in the feather. Each feather is a masterpiece of design. A strong central shaft with interlocking barbs creating a surface that is both flexible and airtight, yet weighs almost nothing. The entire wing is an overlapping cascade of these remarkable structures, creating a large surface area that can be precisely controlled and even repaired one feather at a time. For bats, the answer was different. They stretched a thin, flexible membrane of skin, called a patagium, between dramatically elongated finger bones. This creates a highly adaptable wing that can change its shape with incredible subtlety, providing unparalleled maneuverability. But building the wing is only half the battle. It must be attached to a body that can support it. The torso of a flying animal must be transformed into a rigid, compact fuselage. The spine, pelvis, and ribs are often fused together to create a solid box that resists the twisting forces generated by flapping wings. This rigidity is essential. A flexible body would simply buckle and absorb the power generated by the flight muscles, wasting precious energy. The entire animal must become a living aircraft, a perfectly integrated system where the chassis is as important as the wings themselves. For most evolutionary lineages, this level of radical redesign is simply out of reach. Evolution does not strive towards a goal. It's really a process of, practical problem solving. It's not about perfection or progress, but about finding workable solutions to the challenges of survival. Every adaptation, no matter how impressive, is simply a response to the pressures and opportunities of the environment at that moment in time. An adaptation as costly and complex as flight won't just evolve because it seems like a good idea. The development of wings, specialized muscles, and the energy demands of flight require a huge investment from an organism. It's not something that happens by accident or for the sake of novelty. There absolutely has to be an intense and persistent environmental pressure, a powerful reason to leave the ground. Whether it's escaping predators, finding food, or seeking new territory, the stakes have to be high enough to justify the risks and costs involved. Without a strong ecological incentive, the enormous costs of developing flight would far outweigh any potential benefits. The energy required to power flight is immense, and the anatomical changes needed are drastic. If the payoff isn't significant, natural selection simply won't favor those changes. The intermediate stages would actually be disadvantageous, and natural selection would quickly eliminate them. Half-formed wings or incomplete flight muscles could make an animal more vulnerable, not less, unless those features provided some immediate advantage. So, a very specific set of circumstances is required to kickstart this incredible evolutionary journey. It's a rare convergence of opportunity, challenge, and just the right genetic mutations, all coming together at the right time. One of the most powerful drivers is the opening of a new ecological niche. When a new resource or habitat becomes available, it can trigger a burst of evolutionary innovation as organisms race to exploit it. The sky itself, represents a vast untapped resource. For millions of years it was a space with almost no competition, no predators, and endless possibilities for those bold enough to enter it. For the first insects, the air was an open highway, free from predators and filled with plant spores and other airborne food. This new dimension offered safety, mobility, and access to resources that were out of reach for their earthbound competitors. Taking to the air gave them access to a world no one else could reach. It was a revolutionary leap, opening up new ways to feed, mate, and escape danger. For the ancestors of birds and pterosaurs, flight may have offered a new way to hunt, allowing them to spot and ambush prey from above or to travel quickly between distant food sources. The ability to soar high above the ground gave them a unique vantage point and a powerful advantage over their rivals, or to chase the flying insects that already dominated the aerial realm. As insects took to the skies, their predators had to follow, sparking an evolutionary arms race that pushed both groups to new heights, literally. Flight really opens up a new dimension for foraging, a world of opportunity unavailable to the ground-bound. It allows animals to exploit food sources that would otherwise be impossible to reach, and to do so with speed and agility. The other great motivator is a matter of life and death: predation. The constant threat of being hunted drives innovation, and for many small animals, the ability to escape into the air is the ultimate defense. For a small animal living in a world of larger, faster predators, the ability to escape into the air is the ultimate survival strategy. It's a way to break free from the limitations of the ground and find safety where few can follow. Some theories suggest that the earliest stages of flight may have begun with leaping or gliding behaviors to evade attackers on the ground. These gliders could cover more distance, steer themselves to safety, or even surprise their pursuers by changing direction mid-air. An animal that could jump higher, glide further, or control its fall better than its siblings would be more likely to survive and pass on its genes. Over time, even small advantages could add up, gradually shaping the body for more efficient movement through the air. Over countless generations, this relentless pressure could gradually shape a simple glide into true powered flight, as each new adaptation builds on the last, refining the ability to launch, steer, and eventually flap wings for lift. Turning a desperate escape tactic into a masterful form of locomotion, flight stands as one of evolution's most remarkable achievements, a testament to the power of adaptation and the endless creativity of life on Earth. One of the greatest paradoxes in the evolution of flight is the problem of the intermediate stages. How does nature bridge the gap between a limb and a wing, between a grounded animal and one that soars through the air? This question has puzzled scientists for generations because the transition is not as simple as it might seem. A fully formed wing is a marvel of adaptation, a structure perfectly suited for flight. But what about a half-formed one? What use is a limb that is neither a proper arm nor a functional wing? The answer is not immediately obvious, and it highlights a fundamental challenge in understanding evolutionary transitions. Evolution works in small, incremental steps, and each step must, in some way, be advantageous to the organism. If a new trait is neutral or harmful, it is unlikely to persist. This means that every stage in the development of wings must have provided some benefit, however slight, to the creatures that possess them. If a proto-wing offers no benefit, if it's too small to fly, but too clumsy to be a useful arm or leg, then natural selection would likely select against it. The animal might be less able to escape predators, less able to find food, or simply less efficient at surviving in its environment. This is the valley of non-functionality, a perilous gap that any aspiring flyer must cross. It's a kind of evolutionary chasm where many potential innovations could easily be lost before they ever have a chance to succeed. How can a creature survive while its forelimbs are in the awkward transition phase? It seems almost impossible, yet somehow some animals manage to do just that. The fossil record hints at these transitional forms, but the details of their lives remain shrouded in mystery. For a long time, this was a profound mystery. Paleontologists and evolutionary biologists debated how such a seemingly disadvantageous stage could persist long enough to give rise to true wings and flight. A creature with nubs for wings would seem to be at a disadvantage, less capable of climbing or grasping than its ancestors, yet utterly incapable of flight. It's easy to imagine such a creature struggling to survive, caught between two worlds and not quite fit for either. However, recent discoveries and new theories have shed light on this crucial phase. Fossils of feathered dinosaurs and early birds have revealed surprising adaptations, suggesting that the story of wing evolution is more complex and fascinating than once believed. Perhaps these early proto-wings were not for flight at all. Instead, they may have served entirely different functions, helping their owners survive in unexpected ways. For the feathered dinosaurs on the path to becoming birds, these developing wings may have been used for other purposes first. They might have helped regulate body temperature or played a role in social interactions within their species. They could have been used for display to attract mates, with bright feathers signaling health and vitality to potential partners. For brooding to keep eggs warm, feathers and proto-wings could have provided essential insulation, protecting the next generation from the cold. Or for providing short bursts of lift while running up steep inclines, a behavior we actually see in modern partridge chicks. These chicks use their developing wings to scramble up slopes, showing how even partial wings can be useful. This concept, known as exaptation, is key. It describes how a trait that originally evolved for one function can later be adapted for a completely new purpose. It's the idea that a trait evolved for one purpose can be co-opted for a completely different function later on. This flexibility is one of evolution's greatest strengths, allowing life to innovate in unexpected ways. The feathers that first evolved for insulation or display were later repurposed to form an aerodynamic surface. Over time, these structures became more specialized, eventually giving rise to the complex flight feathers we see in birds today. The limbs that helped a small dinosaur scramble away from danger became the engines of powered flight. Through countless generations, small changes accumulated, transforming awkward forelimbs into the wings that would one day conquer the skies. The evolutionary pathway to the sky is not a straight line. It twists and turns, full of dead ends and unexpected detours, shaped by chance and necessity alike. It is a meandering, opportunistic journey where structures are repurposed in novel ways. Evolution is not a process of perfect design, but of creative problem-solving, making use of whatever is available. Without a useful part-time job for the developing wing, the journey would likely end before it ever truly began. The story of flight is a testament to the power of adaptation and to the remarkable ways life finds to bridge even the most perilous gaps. Long before any vertebrate animal dared to dream of the sky, it belonged to the insects. These tiny creatures were the original masters of the air, soaring through prehistoric landscapes while the rest of life remained earthbound. Their story is one of innovation, adaptation, and a relentless drive to explore new frontiers. They were the first, taking to the air over 400 million years ago, and in many ways they remain the most successful aviators on the planet. Even today, their aerial feats are unmatched in diversity and complexity, from the delicate flutter of a butterfly to the rapid darting maneuvers of a dragonfly. Their pioneering success can be attributed to a unique set of pre-existing advantages that made the leap into the air far less daunting for them than for any other group. Insects were perfectly poised to exploit the skies thanks to a combination of evolutionary quirks and fortuitous adaptations. Their small size was a critical factor. Unlike larger animals, insects could take advantage of the physical properties of air in ways that made flight not only possible but efficient and sustainable. Being small meant that the pull of gravity was weaker and the forces of air viscosity were stronger, making it much easier to generate sufficient lift to become airborne. For them, the sky was not a barrier but an open invitation. Furthermore, their fundamental body plan was serendipitously well suited for the task. The basic architecture of an insect's body provided a natural framework for the evolution of flight. Insects already possessed a rigid, lightweight exoskeleton made of chitin. This remarkable material is both strong and flexible, offering protection without sacrificing mobility. This external skeleton provided a strong, waterproof fuselage and ready-made attachment points for muscles without the need for a heavy internal bony skeleton. It allowed insects to remain light and agile, perfectly suited for aerial maneuvering. Some theories even suggest that their wings did not evolve from legs at all, but as entirely new outgrowths from the thorax. This evolutionary innovation set them apart from other animals that would later attempt flight. This would mean they did not have to sacrifice the function of a pair of limbs to create wings, neatly sidestepping the intermediate stage problem that vertebrates faced. Their six-legged design remained intact, giving them both stability on land and freedom in the air. They could keep all six of their walking legs while developing a completely new set of appendages for flight. This unique solution allowed them to thrive in both terrestrial and aerial environments, a dual mastery that few other creatures could claim. This head start allowed insects to conquer and dominate the aerial ecosystem for over 150 million years before the first pterosaurs arrived. For eons, the skies were ruled by insects alone, their buzzing wings filling the air above ancient forests and swamps. They diversified into a bewildering array of forms, mastering hovering, high-speed flight and intricate acrobatics. Some became expert hunters, others pollinators, and many evolved dazzling colors and patterns to communicate or evade predators. Their presence profoundly shaped the world. Insects became the architects of the aerial ecosystem, influencing the evolution of plants and animals alike. They became the first aerial pollinators, predators and prey, creating a rich ecosystem in the sky that would later provide the very incentive for vertebrates to follow them. The intricate web of life they spun in the air set the foundation for future evolutionary leaps. The insects didn't just evolve flight, they created the aerial world as we know it, setting the stage for all the flyers who would come after. Their legacy is written in every fluttering wing and every buzzing meadow, a testament to the power of innovation and adaptation in the story of life on Earth. So, we return to our central question: why is flight so rare? The answer, as we've seen, is that it demands nothing less than a biological miracle. It is not a single adaptation, but a cascade of perfectly synchronized revolutions. It requires a complete overhaul of the body's structure, from hollow bones to a rigid torso. It requires a metabolic engine capable of sustaining an almost impossibly high energy output, an expense most life forms simply cannot afford. It is a feat of engineering that demands wings that are both feather-light and immensely strong. To achieve all of this is to win an evolutionary lottery of staggering odds. The journey to the sky is only ever undertaken when the ecological pressures are immense, when the rewards of a new food source or a foolproof escape from danger are great enough to justify the immense cost. And even then, the path is blocked by the perilous valley of intermediate forms, a hurdle that can only be crossed if evolution is lucky enough to find a secondary use for a half-made wing. In essence, evolving flight is like asking biology to build a jetpack from scratch. It's a challenge so profound that in 4 billion years of life, only 4 distinct lineages, the insects, pterosaurs, birds, and bats, have ever truly managed to solve it. Each of these groups represents a rare and precious victory over the immense forces that keep life bound to the Earth. They are a testament to the extraordinary and occasionally improbable power of evolution to overcome the ultimate challenge. Like and subscribe.